today we're talking about blocking. Stupid projector. I think my batteries need to be swapped from the remote. Okay. So our first definition is completely randomized design. This is when the experimental units are assigned to the treatments completely by chance. Okay. So a block is a group of experimental units that are known before the experiment to be similar in some way, and it's expected to affect the response to the treatments. So let's say I wanted to do an experiment and I need, I don't know, I'm going to conduct an experiment, but I need to do something during your free time. If I broke you guys up into like seniors versus juniors, seniors versus freshmen, seniors might have less free time because they all have jobs. Or alternatively, seniors might have more free times because they have less hours in school. So. Okay. So the next one is a randomized block design. It's a random assignment of experimental units to treatments, and it's carried out separately within each block. So let's say I was breaking my groups into like seniors and freshmen. In my seniors, I'd be like having one group where I have them, let's say, do extra sports, and the other group is like my control group where they just do nothing in their extra free time. So within each group, you're breaking it up more. A matched pairs design is a common design for comparing two treatments that uses blocks of size 2. There's a lot here, so I'm going to break it up. Okay, so in some matched pairs designs, the two very similar experimental units are randomly assigned within each pair. So a common example of where you would see this is like when they do studies on twins and they do one thing to one twin and something else to another twin. Because twins are usually very similar. Crazy. Okay, and then there's still a little bit more to this. In others, each experimental unit receives both treatments in a random order. Okay, so we have an example here. It says, many students enroll in prep courses to improve their SAT scores. 20 students who have taken the ACT once have volunteered to participate in an experiment comparing online and classroom prep courses. The first one wants me to describe how we can do a completely randomized design to compare online and classroom's SAT prep courses. So this is just like how I would do any other random sample, except now we're actually in the experiment where I'm changing things. So I would still number my students from 1 to 20. And then I could use my random integer to get 10 people. Then the first 10 students selected will take the online course, and the other ones not selected will take the classroom course. So I have 20 volunteers, and 10 of them are in pre-calculus, 6 are in algebra 2, and 4 are in geometry. What kinds of problems would this cause?
Different levels of knowledge for the math portion of the test.
But I'm trying to compare their original SAT score to a retake score after they take this course. Okay. Okay, so how can I fix this problem? Mm-hmm. Yeah, so I could break them up into blocks for pre-calculus, algebra 2, and geometry. So I can compare all the geometry kids together, all the algebra 2 kids together, and all the pre-calculus kids together, because they're kind of alike. Does anyone still need this up? Okay. So on number 3, I have the results of the experiment using the math level as a blocking variable. It wants us to make a dot plot to compare the improvements of the students in the online course and the improvements of the students in the classroom course. And then based on the dot plots to decide if there's convincing evidence that the online course is better. So what I'm going to do is I am going to draw out a dot plot from 0 to 100. And then I'm going to have 2 rows across. I'm going to have online and classroom. And these are my treatments. Then I want to go plot dots for whether they were online or in the classroom. So my first one is online, and they got 100. Second one, online and 100. Third one is 90 online. Fourth one is also 90 online. Fifth one is 100 online. Then I have someone in the classroom. I'll do these in red. So I have 70 in the classroom. I have another 70 in the classroom. I have an 80 in the classroom. Another 80 in the classroom. And a third 80 in the classroom. Then I have a 50 online. A 60 online. A 40 online. And then I have a 30 in the classroom, a 40 in the classroom, and a 20 in the classroom. I have a 30 online, another 30 online, a 0 in the classroom, and a 20 in the classroom. Did I not? You're right. I put them in the wrong spot. Okay, so what do you think looking at these two dot plots? Can I for sure say one's better than the other? Because it's got like drastic differences, right? So So, I'm trying to figure out what I wrote. There is a lot of spread between the average improvement for both courses. So it may not be statistically significant when I find the average. Okay. So in number 3, Chris was saying we ignored the math level of the different students. So we have the dot plot again with different symbols for different math levels. The triangle is pre-calc. The circle is algebra 2. And the square is geometry. Okay. So, looking at these based on their shapes, within each math level, the online students clearly did better than the classroom ones because each of the dots are moved over for each of the groups. So the geometry kids move over, the algebra 2 kids move over, and the pre-calculus kids move over. So we didn't see this difference before because of the variability created by math class. The average improvement for pre-calculus students was 86, and the average improvement for algebra 2 students was 40. And the average improvement for students in geometry was 20. So what we can do is we can use these differences to level the playing field. So what I can do is I can subtract. I'm going to do 66 from pre-calculus. And the reason I'm doing calculus, the reason I'm doing 66 instead of 86 is I did the 86 minus the geometry average to get that 66. Okay, and then I can do the same thing for algebra 2. So I'd subtract 20 from algebra 2. Because I'm taking that 40 and subtracting 20. Okay, so I want to go ahead and actually subtract these numbers from each of the ones. The P's are pre-calculus, the A's are algebra 2, and G is geometry. So on all of my pre-calculus ones, I want to subtract 66. What is 100 minus 66? 34. Okay, so I have 200s. So that's going to be two 34s. Then I have a 90, so 90 minus 66 is 24. And there's two of those 90s. I have another 100, so that is 34. I have a 70, so I want to subtract 66. 4. Another 70, so another 4. And 80, so 80 minus 66. 14. Two of those, actually 3 of those 80s. Okay, then I have an algebra, so I want to subtract 20 from algebra, so 50 minus 20 is 30. And then 60 minus 20 is 40. 40 minus 20, 30 minus 20. I have a 40 minus 20, and a 20 minus 20. And then all of my geometry ones are going to stay the same, because I'm trying to match these to the geometries. Okay, so then the final thing we want to do is we want to do another dot plot. I'm going to do it on the bottom of this page. If you don't have room, there's bottom. There's bottom. There's room at the bottom of the next page. And on this one, I'm going to go from 0 to 40 because my highest number on the adjusted improvement was 40. Oops, I didn't mean to write 40 on the line. Okay. So now I want to actually go put my dots on this graph. I have an online at 34, another online at 34, an online at 24, another online at 24, another online at 34, a classroom at 4, another classroom at 4, a classroom at 14, 3 classrooms actually at 14, then I have an online at 30, an online at 40, an online at 20, a classroom at 10, a classroom at 20, and a classroom at 0. Then I have an online at 30, another one at 30, and then a classroom at 0, and a classroom at 20. Okay, does anyone still need this up? Okay, so what is the benefit of blocking?
Because you know it's accurate, so it's more representative, because then you're putting it into groups based off of, like, each subject, I guess, if you're using the math one.
So it's like accounting for different sources of variability, because obviously I wouldn't want to straight up compare people in geometry to people in pre-calculus. So, in general, we can determine which variables might be best for blocking. You'd want to try and group them together. I don't know what I'm trying to say here. You want to group them together based on how you think they might affect the response variable, and you're just predicting this. So each thing in my group should respond similarly to each other, but differently from other blocks. So like in the math ones, even though the geometry groups didn't show huge improvements, they were similar to each other.